So just a second ago, I started this and then the feed dropped out. So we are doing lesson 7.2. And earlier today in class, the objectives and the recall were on the board, so hopefully you got a chance to copy those. If you did not, they are now in the bottom left-hand corner. Okay, so we're going to talk about how can we use functions to solve equations that only have one variable. So rather than working with an x and a y, we're going to be in situations where there's one variable that we're concerned about, and we're going to be using functions to solve a problem. Okay, and so specifically we're going to look at how do we use intersections to solve an equation, intersection points in lines, and how do we use intercepts to solve equations. Okay, and so remember that the graph of a function is a collection of points, and all those points have an x-coordinate and a y-coordinate. Okay, so it's a collection of points all with an x-coordinate and a y-coordinate, and all non-parallel lines, so as long as the lines aren't like this or like this, have a point of intersection. So as long as the lines are not parallel, you can take them out and somewhere they will have one point of intersection, somewhere where the lines are on top of each other. And finally, you find an x-intercept and a y-intercept by plugging in 0 for the opposite variable. So you find the x-intercept by plugging in 0 for y, or you find the y-intercept by plugging in 0 for x. Okay? So that is your recall. So I'm going to check one more time to make sure the feed is still good, and then we'll get started. Great. It looks like this time we are still good. So the last time I did this, I went and I checked and the feed had dropped out. So we're going to look at two examples, and this is what I want you to put in your notes. After you've put the objectives in the recall, I want you to have all of this in your notes. So here's a situation where some lady named Susan has 3 children, and she's looking to hire a babysitter. And there are 2 babysitters named Babysitter A and Babysitter B. Okay? Babysitter A, her cost, her rate of pay, is calculated by $10 per child plus $5 per hour. So Babysitter A costs $10 per child. So since there's 3 children, it'll be 10 times 3 children is $30. And then on top of that, $5 per hour. Okay? Then Babysitter B has a similar pricing structure. This babysitter has $15 per child and $2 per hour. So it'd be, in the case of Susan, who has 3 children, it'd be 15 times 3 children plus $2 per hour. Okay? So the question is, when will the 2 babysitters cost the same? After how many hours will their cost be exactly the same? Because you notice, with 0 hours, Babysitter B is more expensive. He or she starts at $15, more expensive. But Babysitter B's rate that he or she goes up is only $2, whereas Babysitter A's rate that he or she goes up is $5, so it goes up faster. So we want to find out when are their rates of pay the same. Okay? So first thing we want to do is write a function rule for each babysitter. So I'm going to use A of H and B of H, where H is hours. Okay? So for instance, A of H equals 10 times 3 plus 5H, $5 for every hour. Okay? Bn, where A of H is total pay for babysitter A. Then B of H equals 15 times 3 plus 2H, where B of H is total pay for babysitter B. Okay? So 10 times 3 plus 5H, again we got that 3 from the number of children that the mother has, and 15 times 3 plus 2H. And the question is, when is their compensation, their total pay, the same? Well, if we want to set total pay equal to total pay, that would be A of H is equal to B of H. So the question is, when does that happen? After how many hours does that happen? I'm going to take my expression for A of H and I'm going to put it right here. And 10 times 3 is 30, so from now on I'm not going to spell out that we're doing 10 times the number of children or 15 times the number of children. So this is 30 plus 5H is A of H. B of H is 15 times 3 is 45, plus 2h. Okay? So we're looking for what value of h makes their rates of pay the same. So we take the function rules that generate how much money they make, and we set them equal. And then we just find the h that we can plug in for h in each situation. And if it makes those equations, if it makes both sides of the equation the same, that means it's made both of their total pays the same. So that's the hours at which they get paid the same. Okay, so let's solve this equation for h. I'm going to subtract 2h from both sides. That's going to leave me with 30 plus 3h equals 45. Then I'm going to subtract 30 from both sides. It's going to leave me with 3h equals 15. Divide both sides by 3. We come up with h equals 5. Okay? So we find that babysitter A and babysitter B make the same amount of money if they babysit 3 children for 5 hours. So both babysitters would make the same amount of money if they both babysit 3 children for 5 hours. Okay? So what we did here was we found a place where these two lines intersect. Okay, so notice if this were the graph of the two rates of pay. Okay, so, and let's say that this right here is y equals 30. So we're just starting at 30. And each of these is 5. Okay, so the babysitter A is right here, starting at 30 with the 3 children, and going up by $5 every hour. Okay, up 5, right 1, up 5, right 1. So this line right here is the rate of pay for the pay for babysitter A. Then this right here is babysitter B. Babysitter B starts at $45. 5, 10, 15 above our starting point of 30. So 5, 10, 15 right here, but only goes up 2 for every 1. Okay, $2 for every 1 hour, right? So a slower increase in pay. And it's over here at 5 hours that they both intersect. It's at 5 hours that the lines are in the same vertical position, with the vertical position being the output, which is the money they make, and the horizontal position being the hours they've worked. It's right here at 5 hours that they intersect. And we can find that using our rules. So we think they make the same amount of money at 5 hours. Okay, whoops. Okay, so let's look at this one. A of h equals 30 plus 5 times 5 equals 30 plus 25 equals 55. Okay, and B of h equals 45 plus 2 times 5 equals 45 plus 10 equals 55. So that means both of these linear functions have a point 555. And that's what we want to find when it asks us when these two are equal. So if you're in a situation where there's 2 ways of calculating a similar output, and it asks you for when they're equal, you just take the function rules and set them equal and solve for the one variable. Okay? So that's one type of exercise we're working on. The other one is this type. So there's a person, she has $2,000 in a bank account. Okay? And a monthly mortgage payment of $900.01. If this person has $2,000 in the bank account and doesn't add anything to it, but just keeps paying her mortgage out of it, the question is, when will she run out of money? Okay? So what we're saying is, if f of x equals current balance in the bank account, then we can model the current balance by saying and x equals number of months, number of payments, Okay, payments made. So we can say f of x equals 2,000, the starting amount of money in the bank account, minus $900.01 for every month, for every payment made. So if they've made one payment, it's $2,000 minus $900.01. If they've made two payments, it'd be 2 times 900.01, which is 1,800.02. Take that off of 2,000, that's what's remaining in the account. Okay? So the question is, when is this person going to run out of money if they don't add anything to the bank account? Well, running out of money means $0 in the bank account. $0 in the bank account. So if we were to call f of x y, okay, we would say, when is y 0? Because we're looking for when the bank account runs out of money. When the bank account, the current balance, hits 0. Okay? That's what we're trying to find out. So essentially, we're looking for the x-intercept. We're saying what value of x will get us a y of 0. Okay? So we plug in 0 for y. And we solve for x. Okay? So we subtract 2,000 from both sides. End up with negative 2,000 equals negative 900.01x. Notice, because over here I was subtracting 900.01, when I subtract away the 2,000, it goes over here. The 900.01 is still negative. So now I divide both sides by negative 900.01. Okay? And I'm left with x being approximately 2.2. Okay? So that means in this equation, if I plug in about 2.2 for x, I'm going to get out a y of 0. But remember, the question was, when does the account run out of money? So these payments don't come incrementally, they come every month, like say the first or second day of the month. And so on month 1, like it's the first of that month, $900.01 comes out. Then in the second month, $900.01 comes out. At that point, there is less than $900 remaining in the account. So on the third draw, the account would go negative. Remember, this is one of those where you have to say, we can't get to 3. There are not 3 payments in the account. So we would say that after 2 payments, the person would have to put more money in the account, because on the third draw, they're going to go negative. Okay? So you'll do some exercises like these in your classwork. So the exercises that go with this lesson are on page 314 to 318, 1 to 4, and 9 to 12. And there's 4 problems that are like this, and 4 exercises like this. So go ahead and make sure you have all of this in your notes, and when I see you next time in class, we'll work on those exercises together. All right? See you later, and happy mathing.